Hello, in this video we are going to talk about channel length modulation and transconductance of most devices. So we already saw in a previous video that the drain current and the voltage of the drain, or the VDS, are related in this form. Initially they are related with this expression ID is equal to mu n Cox W over L VGS minus VTH, bigger bracket here, VD minus 1 over 2 VG 1 over 2 VD squared, VDS squared. Okay, hope I'm right on this. And we said that the maximum of this expression is given when you differentiate this and equate to 0. And we also realize that the maximum point will occur when VDS is equal to VGS minus VTH. And beyond that voltage, we said there was saturation. Okay, but ideally we would have a straight line, meaning the voltage doesn't change beyond this point the current doesn't change beyond this point with respect to VDS. So you can check out the last video in the playlist if you missed out these. Now we are looking at what really happens, just like in the most devices, the BJTs, when we had early effects. We have what we call channel length modulation here. As the voltage between the drain and the source, or the potential difference between the drain and the source, or the drain voltage increases, then beyond this point there will be a pinch off. So at this point, when VDS is exactly equal to the overdrive voltage, that's VGS minus VTH, we have the pinch off being created just at the edge. So assuming this is my channel, and with a gate, okay, so that wasn't really well drawn. So assuming this is a channel, okay, so I have the pinch off here when VD is equal to VG minus VTH. But as I further increase VD, then the pinch off would also further increase to the left. And that means that the length, or the effective length of the channel, reduces. We earlier on said, or even from the equation, we can tell that as the length reduces, because the pinch off now has pushed to the left, then the current would also increase slightly. So you see there is a slight dependence of the current on VDS after saturation, which is not ideal for a current source. For a current source, we need this to be as flat as possible. The only advantage we have here over the BJT is that with the MOS device, we have control over the length in our design. So assuming the length is relatively longer, so you can see here, if the original length is relatively longer compared to the original length L1, then a change in the channel length would affect the IDS less as compared to a shorter length. So you see, assuming it's a ratio, there's a ratio in the change, and let's assume the original length were 100 meters here, which is just extreme because we are dealing in micrometers. So let me just put okay, so assuming you have a length of 100 meters, and here you had a length of 50 meters or 50 micrometers, still too big. Okay, so if by channel length modulation, as I increase VDS, the pinch off occurs here, just say 2 micrometers. The same effect, the pinch off occurs here, 2 micrometers. So the ratio of the change here compared to this will give a higher effect of the channel length modulation on the current as compared to what will happen on the current. So you can see the difference in the two curves. Here, channel length modulation is affecting the current more as compared to this one. So to model or to account for channel length modulation, which only can occur after saturation, we take the equation for drain current after saturation, which is 1/2 mu n Cox W/L VGS minus VTH square. Then we put another factor that would account for the slight changes that the VDS has over the ID. Remember, in early effect, we put 1 plus VCE over the early voltage. So this time around, what we do is, so the same way, this term here had no unit because voltage would cancel out. So it would just be a factor multiplying the IC in early voltage in BJTs. But for most device, what we do is we put 1 plus VDS, and instead of VA, we put lambda here. So the lambda is the coefficient of channel length modulation, just as VA is specified. So if there's no channel length modulation, we say VA is infinity, which makes all this term 0. In this case, when there's no channel length modulation, we say lambda is equal to 0. So based on this, we can get the model or the large signal model of the MOS device. So with channel length modulation, of course, there should be VGS greater than the threshold voltage, and once there is saturation, that means we go beyond the overdrive voltage, the VDS is above the overdrive voltage, then this will be the right equation or the right model. So you have the gate source voltage with an open circuit showing an input impedance of infinity here, and changing the VGS affects this as a current source with this equation here. So this is a more precise equation taking channel length modulation into account. So you see that this current source is not really ideal because slightly depends on the value of VDS. Okay, and another situation, this in the triode region or before we reach saturation, the original equation holds. So this is the original equation before saturation. So VGS affects it in that way. And when VDS is really small, we said in that instance, we have almost a linear dependence between the current and the drain voltage. So when VDS is very small, this term becomes really small, so we can neglect that term and have the equation this way. So when you plot the curve, we are looking at the beginning part, which is approximately depending on this side of the equation. Okay, so you are used to maybe putting this inside and canceling these two, and it's the same thing. So when you write it that way, then you can model that part when VDS is really small, smaller than twice VGS minus VTH over drive voltage. Okay, so in that case, you can model it as a resistor because it behaves as a normal resistor, and the value of the resistance would be given as 1 over this term over here. So how did we come across that term? if you plot a curve which looks like this, and this VDS and this is ID, we said at the early part of the curve we just take the linear side of the equation. So it's approximately ID at this point when VDS is far less than twice the overdrive voltage. We can approximate the original equation and just take the linear part, which goes like mu W over L, so Cox mu n, then just VG minus, so VGS minus VTH VD. So this is the x-axis and this is the y-axis. So the slope, if I compare that to y is equal to mx plus c, since we are starting from 0, this is gone, and the slope of the curve becomes this. But since it is not a voltage current curve, but rather a current voltage curve, the slope is not resistance, the slope becomes 1 over resistance. So this value becomes 1 over resistance. That means that the resistance itself would be 1 over all that we have here. So you can model this. So if you want to model this, you just model it as a form that changing the VGS affects the current, but in a normal sense, like a resistor, because you have a straight line, and you have a straight line, it just becomes a linear device which obeys Ohm's law, and the value of the resistance is as shown and also explained earlier on. Then finally, we look at the transconductance of the device. So we said that you could operate the device as a current source, voltage dependent current source, and when you operate the device as a voltage dependent current source, then you can build an amplifier out of it. So in the next video, we will take a closer look at the transconductance and how we came about all these formulas. Until then, see you. Bye.